All right, so last time we were talking about Lewis dot structures, and we had done a worksheet over Lewis dot structures. It was very comprehensive, and so I thought instead of looking at the PowerPoint's sort of lacking in detail, so I thought I would just kind of scroll through the chapter sections to give you guys an overview of Lewis symbols and drawing out Lewis structures for compounds. And so here in your textbook, it's showing you Lewis symbols, and of course, if you look at the electron configuration for different elements, you will see how many valence electrons each element has. And of course, the dot in a Lewis symbol or Lewis dot structure represents the valence electrons, the number of valence electrons for that element. And so for sodium, for example, its electron configuration, um, the valence electron part is 3s1, and so the subscript number is 1. There's one electron there, and so it has one dot. For magnesium, it's 3s2, so 2 electrons, 2 dots. 3s2, 3p1, so 2 plus 1 is 3, 3 dots for aluminum. You can also see that on the periodic table. For example, sodium's in group 1, or if you look at your periodic table, the old-fashioned numbering system 1A, magnesium is in group 2A, aluminum is in group 3A, the new numbering convention is 13, but the old one is 3A. Silicon is 4A, phosphorus 5A, and so on. And so you see with electron configurations, here if you're writing the electron configuration using a noble gas, starting with a noble gas instead of hydrogen, you can see just the valence electron configuration here that's shown there. And so you can see the Lewis dot symbols are pretty easy to write for individual elements. And then here they're showing you how you have Lewis dot structures can show you how an element loses or gains an electron. Okay, and you can see that here where sodium lost its one valence electron to form a cation. Okay, and chlorine gained an electron to form an anion. And then you can see further down here how sodium and chlorine, using Lewis symbols here, how when they come together they form an ionic compound. And you can see that with these other elements here, how you can represent a formation of an ionic bond by showing Lewis structures. And so that's what they're showing here. So when you're talking about compounds, so or even molecules, Lewis structures become a little bit more complicated to draw out. And so here you see a simple structure where you have 2 chlorine atoms. Chlorine is in group 17, so it has 7 valence electrons, and each atom can basically share an electron because each atom wants 8 valence electrons. And so it already has 7, it needs one more, so they each share one. Okay, and then with Lewis structures, when we have a sharing of a pair of electrons, we draw out a single line, and that represents a single covalent bond between these 2 atoms here. Okay, so here we see hydrogen with the same issue. Hydrogen is unique in that it's in group 1, so it only has 1 valence electron. And if you remember, its electron configuration is 1s1. Okay, to have a full shell, it only needs another electron. So hydrogen is weird in that it only needs 2 to have a full shell, whereas the other ones need 8. All right, so that gets us to the octet rule, and of course, with the octet rule, basically every electron or every element wants 8 valence electrons. Okay, it's known as the octet rule. It wants basically a full shell, And so we get 8 from the S subshell, which takes up 2, and the P subshell, which takes up 6. So 6 plus 2 is 8. Now you may say, well, what about the other elements that have D and F subshells? And for those, like most things in chemistry, the octet rule doesn't apply for every element on the periodic table, but it applies to most of the ones that we end up talking about in general chemistry. And so for most of the compounds that we deal with, the octet rule will apply. So here we have several different compounds here. We have carbon tetrachloride. And so carbon has 4 valence electrons. Okay, chlorine has 7. Okay, so it has 1 more. And so basically carbon, and when you take organic chemistry, you'll see that carbon forms 4 covalent bonds always. Okay, so it's usually the backbone of some sort of structural component. And so we see here carbon being in the center. And usually when you have halogens, a multiple number of halogens, they're going to be terminal atoms. Terminal atoms are the atoms outside, and they have to obey the octet rule. Central atoms usually obey the octet rule, but not always. They can have fewer than 8 or more than 8. Okay, so we'll go through some examples later on that shows you the molecules that have exceptions. All right, so here we see chlorine, again, has 7 valence electrons. And remember, every line represents 2 electrons. So one's from chlorine and the other one's from carbon. So carbon has 4 electrons, okay? And then chlorine has 7. And so again, carbon forming 4 covalent bonds, each bond with a different chlorine atom. Here we see silane. So silicon has 4 valence electrons, and so hydrogen only needs an electron to form 2, so hydrogen should have 2 electrons around it. And so you see here that hydrogen is going to have 2, and the silicon is going to have 8, 2, 4, 6, 8, because it already has 4, and then it's sharing 4 with hydrogen. And so again, notice that every element in this scenario has 8 valence electrons around it, with the exception of hydrogen, which has 2, which completes its S subshell. All right, so I'm just going through this because I know we've already done Lewis dot structures for these compounds. I'm just going through a little bit of the explanation as to why they're drawn the way they are, and then I didn't technically go through some of these rules that we should probably go through if you're new to this, and you're maybe should write down the rules and go through it systematically, go through a systematic process, and that way you can sort of learn how to write Lewis structures that way instead of just kind of jumping into it. So here we see the structure for ammonia. Nitrogen has 5 valence electrons, so 1, 2, 3, 4, 5, and then hydrogen has 1, so it's going to form, hydrogen usually is going to form a single bond with a central atom, and it's usually again a terminal atom. Even especially if there's an oxygen, it's usually bound to oxygen, and there's a terminal atom there. It cannot be in the center ever, because if it was a central atom, that would imply that it could have more than 2 electrons around it, and we know hydrogen can only have a maximum of 2. So hydrogen is generally a terminal atom. Here we see water, where oxygen is in the center. Oxygen has 6 valence electrons, so it has 2 that are shared between hydrogen, and then it has 2 lone pairs. Okay, so that makes 6. And then all around hydrogen you have 8, 2, 4, 6, 8 electrons, and then you have 2 around hydrogen, each hydrogen atom. Hydrogen fluoride, also known as hydrofluoric acid. Fluorine has 7, so you see 2, 4, 6, 7, and then there's 1 here from hydrogen. So there's 8 total around fluorine, and then hydrogen has 2. All right, so we really didn't talk about double and triple bonds in detail. A double bond is basically 2 pairs of shared electrons. So here you see formaldehyde, where you have hydrogen, you have carbon in the center, and then you have this carbon-oxygen double bond. And so the reason for double bonding is this. Normally you have oxygen, you have like, you'll have lone pairs around it. But carbon is going to, if it doesn't have a double bond, remember carbon needs 4 bonds, right? That's just the way carbon works. It always forms 4 bonds, 4 covalent bonds. It doesn't matter if they're double bonds, single bonds, triple bonds. It needs 4 because it has to have, remember, every line is 2 electrons, so it needs to have 8 electrons around it in order to satisfy the octet rule. So what you end up having to do is to make a double bond in order to have 8 electrons around carbon. Okay, and so you basically you're taking off some valence electrons from oxygen in order to do that. Okay, so now carbon is happy. Oxygen has 2, 4, 6, 8, also has 8 around it, and so it's happy. And so what you'll see is you'll start with single bonds when you're drawing out Lewis structures, and then you end up having to form a double bond in order to try to make sure every element has 8 electrons around it. And so that's what you end up seeing here when you have to make a double bond. Ethylene, here we have a case again where we have carbon where it only has 3 bonds, and so it needs an extra bond in between there. And if we look at the electrons from carbon, it has 4, 1, 2, 3, 4, 1, 2, 3, 4, and then hydrogen has 1 each. Okay, so you end up having to have a double bond between each single carbon atom, okay, in order to satisfy the octet rule. Now, sometimes you can draw out a triple bond. A triple bond is when you have 3 electron pairs. Okay, so here you see 3 electron pairs. That represents the triple bond there. And then you see a lone pair on the carbon and a lone pair on the oxygen. So why do you do this? Well, carbon's going to have, it needs 4 covalent bonds. Now, I said that, and now I'm going to say that, of course, it's not always that way. It has to have 8 electrons around it. In this case here, it has 3 covalent bonds, okay, all 3 with oxygen, but it does have this lone pair, so that's, you can count that as it's an electron pair, so it's like kind of like a covalent bond in a way. So here you see that carbon has 8 valence electrons, 2, 4, 6, well, 8 valence electrons plus shared electrons, 8 electrons around it to fill its subshell. And then oxygen also has 8, 2, 4, 6, 8. Okay, so if we want to count the electrons from carbon, it has 4, 1, 2, 3, 4, and then oxygen has 1, 2, 3, 4, 5, 6. And so you see how you have originally a little bit more, 1 more electron by carbon than you would normally see. And we're going to talk about that. It's called formal charge. And we're going to talk about how to assign formal charge. If you did the lab on Wednesday, you probably already have a good idea on how to assign formal charges to elements in a compound, and how that dictates which Lewis structure is correct, because sometimes you can get to a point where you have 2 Lewis structures that are actually correct, and so you have to figure out which one is more likely to be the correct structure. And so you do that, you figure that out by assigning formal charges to each element in the compound. So here we have an example of the cyanide ion. And so again, carbon has 4 electrons, 1, 2, 3, 4, and then there's 1 from nitrogen. So 1, 2, 3, 4, 5, 6. Normally nitrogen only has 5, but you have that extra one because there's a negative charge there. Now when a structure has a negative charge, there's an extra electron there, and it's not really assigned to a specific element. So it can be wherever it needs to be, and most of the time you're going to want to put it at a point where if there's a lone pair or a single electron, you want to make sure that single electron is paired off so that it's a lone pair and not a single odd number of electrons. Because I don't know if you noticed or not, but when you count the number of electrons you should have for each structure, it's basically usually an even number. And so if you have extra electrons, they're lone pairs and they're not single electrons on an element. You don't ever want to see that. Now again, there are exceptions, but the exceptions are not as common as you would think.